Hi everyone, I'm Zhengxiang Zhou from City University of Hong Kong. Today I'm presenting No-Fuzz, efficient anti-fuzzing technicals. Fuzzing has achieved great success in recent years and has found a large number of bugs. On the one hand, developers can fuzz the program to find bugs and report the bugs to the companies, and the companies can fix them before they are open to the public. However, the attackers can also fuzz the program to find zero-day vulnerabilities, and even worse, they can exploit the bugs to cause financial loss to the companies. So there is a need for anti-fuzzing technicals. And the purpose of anti-fuzzing is to prevent the malicious use of fuzzing. And here is how it generally works. So we compile the source code of the program into two versions. The one version is protected by the anti-fuzzing code, and the other is the normal one. The protected version will be released to the public, including the users and the attackers, and the trusted parties own the normal version. So the attackers can fuzz the protected program, but they can only find a few bugs because of the anti-fuzzing defense. And the trusted parties can also fuzz the program, but they can find more bugs and earlier than the attackers to avoid zero-day vulnerabilities. So here I will introduce some categories of existing anti-fuzzing technicals. And the first is called target detection. So it identifies fuzzers by their unique runtime information. So for example, the environment variables, the process names, and the input file names, and etc. So here is an example of identifying the famous fuzzer AFL by its environment variable. So this, which is the double underline followed by AFL. And the second category is to introduce latency. So introducing latency not only affects fuzzers but also normal users. The challenge is where to insert latency that only prevents fuzzing but has insignificant impact on normal users. So existing solutions try to insert the latency into code blocks where normal users will rarely reach these blocks, like some manually located error handling blocks, or just finding some code blocks based on binary analysis technicals. And the third method is to utilize the coverage feedback mechanism of fuzzers. And the coverage information is stored in a bitmap of fixed size. Mostly, new coverage information can be regarded as the edges connected blocks in control flow graphs. So this method adds a large number of fake blocks into the program, and fuzzers will record the fake coverage information into the bitmap. If the number of fake blocks is large enough, the coverage bitmap of fuzzers will be saturated with fake information, and it will be no longer to identify new coverage in the original program. And also there are some other types of anti-fuzzing technicals, like to disturb the data flow of the protected program, to prevent taint analysis and symbolic executions. But these technicals are out of the scope of this work, so I will skip them here. And the aforementioned technicals seem to be promising, but they still have some drawbacks. So first, the targeted detection can only defend a few fuzzers, and the unique runtime information can also be easily changed. And the second is, it is not convenient to use these technicals, as there are many manual efforts required to determine the code blocks and like the error handling blocks. And third is that the actual storage cost for anti-fuzzing codes, especially for fake blocks, is too large, which is about 20 megabytes for a small program, while these small programs may take only a few megabytes. So we consider these technicals are not practical, and we want to design the more general technicals, and they are more easier to use with smaller storage cost. So here comes to our design. We designed 3 new anti-fuzzing methods. 2 of them are the passive detection methods, and 1 is the optimization of private fake blocks. So unlike the targeted detection, passive detection can precisely identify the running environment of the protected program, and they can inform whether there exists a fuzzer or not. So the first method is to utilize the timing gap between normal execution and that with a binary-only fuzzer. So here is an example. Suppose the green code in the figure on the left takes 10 milliseconds, and this code will be close to the running time of the red instrumentation on the right. And however, in the binary-only fuzzing mode, the execution of the instrumentation will usually take more time than that in the normal execution, which will be larger than the 10 milliseconds. So we assume it takes 20 milliseconds. So we can compare the time of the executions of instrumented, which takes 30 milliseconds, and uninstrumented codes, which only take 10 milliseconds, to identify whether there exists a fuzzer or not. And the second method is to monitor the execution frequency. So this method is based on the assumption that a normal user will not repeat a program for too many times within a short time period. So otherwise, if we found a program has been repeated for too many times within a short time period, we can claim that there exists a fuzzer. And here is an example. So if the protected program runs normally, every time it runs, it creates a daemon process and a temporary file somewhere in the system. So the file will exist for a certain time period. In this example, we define it to be 30 seconds. And the daemon process will store the information of the file, including the location of the file and an ID for the file, standing for the ascending order of its creation. And in other words, one daemon process manages one temporary file. And if the program has been rerun within the time period, so it creates another file and another daemon process. So suppose in this example, it has been run for 4 times in 30 seconds. So it will in total create 4 temporary files and 4 daemon processes. And after the 30 seconds, the daemon process will delete its corresponding temporary file and execute normally. And also this is the same for other files. So this is how it works for normal execution. However, when the program is run by a fuzzer, because a fuzzer will run the program for too many times within a short time period, so it will create too many files and also the daemon process. And until it reaches a threshold. If we define the threshold to be 100 in this example, so we will be informed that this program has been rerun for 100 times within 30 seconds, and we think it's abnormal. So we will trigger the anti-fuzzing mechanisms like introducing latency into the program or just aborting the program. The third method is the optimization of the private fake blocks. So this optimization optimizes the storage overhead. We add a code snippet which consists of many 1-byte instructions before the start of the original function. And we call this region the landing space. And these 1-byte instructions will not affect the normal execution of the program. And we then further modify the original function call, that every time the function is invoked, the control flow will land at a random byte in the landing space. Since the fuzzer recognizes new coverage by the edges, so it will identify every byte in the landing space as a new block and record the fake coverage information. And if the protected program has been run for sufficient times, every byte in the landing space will be recognized as a fake block. And with the landing space, we reduce the storage cost of 1 fake block from a function to only 1 byte. However, the naive landing space also has some problems. So the first is the execution of unnecessary instructions. So here is an example. If the control flow lands at an early address in the landing space, suppose the first one in this example, it will have to execute all the rest instructions to reach the start of the original function, and which should be considered unnecessary. So to handle this problem, we modify some 1-byte instruction to 2-byte jump instructions. And if the control flow lands at the jump instruction, the jump of that will be the opcode of the next instruction. Also, we will make sure that the destination address will be within the landing space. And in this example, it will jump over 54 bytes. And when the control flow lands at the second byte, which is also the jump offset for the first instruction, it will be recognized normally as an exclusive OR operation. And if we can insert enough jump instruction into the landing space, most unnecessary blocks will be skipped. Another problem is that we find the high addresses of landing spaces are close to each other, because many fuzzers are using exclusive OR to update the coverage bitmap. So it will be likely to cause hash collisions, which can also reduce the number of fake blocks generated by the landing space. So to handle this problem, we abandon the landing space occupying a large space. Instead, we create many intermediate functions chained to the original function. Each intermediate function only has an empty function frame with small landing space. Since the high address of each function is different, so it will be less likely to cause hash collision. So here comes to our evaluation. We evaluate all the three and the combined technicals separately against 5 famous binary-only fuzzers. And the results show all of our technicals are effective at reducing the coverage, while the combined one is the most effective one, which is the yellow one in this figure. Also, there are more evaluations to show that the anti-fuzzing technicals can hinder or prevent the bug fighting in a lava benchmark. And if the fuzzer cannot find a bug within 48 hours, we give it a check mark here. Moreover, we also calculate the anti-fuzzing efficiency to demonstrate our technicals can achieve the same level of defense as private works. And our works can achieve the defense with even lower overhead. So in summary, we contribute 3 new anti-fuzzing methods: the 2 passive detection methods against binary-only fuzzing, and the passive detection can precisely identify the existence of fuzzers. Also, we have contributed the landing space, which optimizes the storage overhead of private fake blocks from 1 function to only 1 byte. Thank you.
Hello everyone, I'm Zhang from Nanjing University. Today, I'm going to talk about my paper, eSROP attack, leveraging signal handler to implement Turing-complete attack on the CFI defense. Here are my collaborators. In this paper, we introduce a new kind of attack called eSROP attack. We will describe the attack from the following aspects. First, we will introduce the background. Return-oriented programming attack is a kind of control flow attack which diverts the program's execution flow. It reuses code snippets in the program to perform malicious behavior instead of injecting malicious code. It has been popular for decades and has lots of variants. Secret return-oriented programming attack is one of the variants of ROP attack. It leverages secret return system call to conduct attack. The attacker sets up a fixed signal frame on stack and invokes secret return system call. When the secret return gets executed, it treats the fixed signal frame as the signal interrupted context and uses it to restore all registered values. After the signal returns, the program will jump to the address that pointed to by the RIP register and continue to execute attacker-controlled instructions. Finally, the attacker can execute arbitrary instructions. In recent years, many defenses have been proposed to defend against SRP attack. For example, signal cookies uses kernel to insert a secret value into the signal frame to detect whether the signal frame has been tampered with. A fixed signal frame cannot pass this detection. PICFI and MCFI propose to inline secret return system call into each signal handler and make the secret return system call unreachable from other application calls. Hence, it prevents SRP from directly invoking secret return function. Other strong defenses such as CFI and shadow stack also prevent our SRP attack. CFI defense enforces the program's execution, not violating a pre-computed control flow graph. Shadow stack defense prevents attackers from overwriting return addresses, so it becomes difficult to conduct SRP attack under these defenses. However, our research shows that by leveraging signal handlers, attackers still possible to conduct attack under these defenses. So we propose eSRP attack. It is a more dangerous variant of SRP attack. It can survive under multiple defenses. The core idea is leveraging the signal nesting mechanism and the vulnerable signal handler to modify non-control data in signal frame. This attack can give attackers the ability to invoke arbitrary system calls, do Turing-complete computations, and bypass a fine-grained level-based CFI defense. In the following, we will discuss our attack assumptions. First, we assume the program is under the following protections: DEP, ASLR, shadow stack, and CFI. Then we assume there is a vulnerability in the program which gives the attacker arbitrary read and write primitive, and the program is dynamically linked. Also, the attacker can send signals to the victim. This assumption is easy to achieve in local attacks. In this paper, we mainly discuss local attacks. We leave remote attack as our future work. Then we describe our attack method. We send a signal when the program is executing some security-critical instructions, such as syscall instruction. We use signal handler to overwrite the on-stack signal frame. The overwriter leaves the control data unchanged and only modifies non-control data in the signal frame. Then, when signal returns, the program returns to the interrupted instruction to continue executing security-critical instruction. Now the register context has been changed. The instruction will do a completely different work. Compare with the SRP attack. SRP directly modifies the return address to invoke secret return system call. This operation can be easily detected by shadow stack defense. eSRP uses a signal handler to overwrite the on-stack signal frame. eSRP sends the signal and returns to the signal interrupted instruction as usual, so it is more stealthy. Meanwhile, SRP modifies the control data in the signal frame. However, EAI only changes non-control data, so EAI can bypass more defenses. This is the whole attack procedure. In our attack, most attack methods is implemented in the signal handler. However, the program's original signal handler won't do the attacker's work, so we change some GOT table entries to modify the functionality of the original signal handler. We need to find suitable functions in the signal handler which will later be replaced by put function and sleep function. In other words, we need the signal handler to invoke put function and sleep function, and put function is executed before sleep function. The reason we choose these two functions is that we leverage put function to first leak the signal frame on the stack. The leaked information contains the current interrupted instruction pointer. The attacker observes the value and decides whether it is the target instruction. If it is, the attacker sends the second signal. The sleep function is used to wait for the attacker's second signal. Once the second signal arrives, the same signal handler responds. This time, put function will overwrite the signal frame with a fixed signal frame. When signal returns, the register contacts have been changed. The attack can be completed. In this attack, we use put function twice, but exploits its different functionalities. For the first time, put only leaks the signal frame. For the second time, it will overwrite the signal frame. The reason that it can have different functionalities in two continuous executions is because the parameter is different in two executions, and the write buffer pointer is changed automatically. Before the put function's first invocation, we set the current write pointer points to the end of the signal frame. The put function considers the output buffer is full, and it will leak the signal frame. After the leakage, the current write pointer will automatically adjust to the start of the signal frame. When the put function is called the second time, it considers that the output buffer is empty, and it will copy the fixed signal frame onto the original signal frame, so the overriding happens. This attack has three application scenarios. When the interrupted instruction is a syscall instruction, the attacker can invoke an arbitrary system call instead of the original one. Because the attack can manipulate the IEX register's value, which stores the syscall number. In the second scenario, the interrupted instruction is a DOP gadget. The attacker can leverage the gadget to implement Turing-complete computation. We find that DOP gadget is more suitable to be our attack targets because different from original ROP gadgets, DOP gadgets requires to deliver operation results with memory, and they need not be executed one after another. The program can execute several other instructions between two adjacent DOP gadgets. This is also work in our attack. DOP gadget is first proposed by DOP attack. DOP attack uses a call snippet to connect DOP gadget, which is called dispatcher gadget. However, the dispatcher gadgets are very rare and sometimes do not exist in a victim program. Even if it exists, it constrains the DOP gadget that attacker can use. In our attack, we use signal to connect DOP gadgets. So we eliminate the need for dispatcher gadget. At the same time, all the DoD gadgets in the program can be used by our eSROP attack, since that DoD gadgets can simulate Turing-complete computation. So our eSROP attack is also Turing-complete. Attackers can also use our eSROP attack to bypass fine-grained level-based CFI defense. The fine-grained level-based CFI rewrites the binary to insert some verification code before each indirect branch. If we send the signal when the program is executing the CFI verification code and uses the signal handler to modify the E-flex register value in the signal frame, we can manipulate the CFI verification result. Then, when the signal returns, the CFI defense is bypassed. The attacker can jump to an arbitrary location. To prevent eSROP attack, it is important to set the GOT table unwritable. Also, other defenses that protect control flow elements can prevent our attack, such as CPI and CPS. To evaluate eSROP, we conduct two experiments. This is our experimental setup. The vulnerable programs are ProFTPD and WFTPD. In ProFTPD attack, we exploit a stack buffer overflow vulnerability. The code snippet is abstract from ProFTPD. The function is the signal handler for SIG-alarm signal. It is registered by the program itself. The attack steps are as follows. We first modify GOT table entries to use the put function and sleep function to replace the SIG-empty set function and alarm function. Then we modify the pointers in the standard out objects file structure to make the put function do the attacker's work. Third, we prepare a fixed signal frame on stack. Then we can send a signal. The signal handler responds. In it, it will invoke put function. The put function will leak the original signal frame. There is a critical data in the output signal frame, the currently interrupted instruction pointer. The attacker can determine whether it is a syscall instruction. If it is, we send the second signal. The same signal handler responds. This time, put function will overwrite the signal frame. When the signal returns, the program will execute ESEC system call instead of original system call. Finally, attacker can get a shell. This is the pointer setting for the put function to work well. Our attack is implemented in a Ruby script. It is invoked by the Metasploit framework. We can obtain a shell. The attack can be completed within 6 minutes. In our WFTPD attack, we exploit a formal string vulnerability. This code is abstract from WFTPD. We leverage this function to conduct our attack. We send a signal when the program has isolated privilege and before it invokes the exec function. In the signal handler, we modify the parameters for the exec function. When the signal returns, the attacker will obtain a root shell. The attack steps are as follows. Our attack is implemented in a C program. It can also be implemented in a Python script. Finally, we obtain a root shell and our attack can be completed in 5 minutes. Thank you very much.
Hello, everyone. Welcome to my presentation. I'm Tong Wei, third-year PhD student, a member of Cake Lab in WPI. Today, I'm going to talk about our paper, Breaking IoT Software Homogeneity with Protocol Mutations. This paper is advised by Professor Lorenzo Di Carli, co-worked with Ryan Williams, Shandu Ganguly, and Professor Long Lu from Northeastern University. In this talk, we will introduce a moving target defense technique, which alters the syntax of network protocols. It introduces protocol mutations at the compile time, so as to protect self-contained IoT deployments like military, industrial, or smart cities. IoT software homogeneity is a phenomenon that oftentimes different devices reuse the same open source components and or are built on the underlying platforms provided by the same manufacturer. From some perspectives, it has advantages like convenience, but large numbers of network-connected devices with homogeneous software stack but poor software quality result in significant replication of the same vulnerability. Researchers and existing reports have shown that a single widespread vulnerability in a highly popular device can enable large-scale attacks and cause significant loss. For example, a single zero-day affecting Huawei home gateway devices enabled cybercriminals to create a 100,000-strong botnet in December 2017. Our paper targets a style of IoT and embedded systems that we term self-contained critical deployments. We define SCDs as deployments, where the set of devices that belong to the deployment is a priori known, and an attacker can communicate to the deployment to cause disruption or even human cost. The reason why we target SCDs is they are self-contained with a single organization, which enables us to change protocol stack without concerning compatibility. More specifically, targets of our paper can be IoT machine-to-machine protocols and other message-oriented protocols like MQTT or lightweight machine-to-machine protocols, which are used widely in practice. Best practice security measures such as robust authentication can help mitigate this risk. But the real experiences demonstrate that they can be bypassed because of vulnerable implementations. Thus, we propose the use of software diversity as an approach that can provide additional security when paired with best practices. The key idea is to mutate the protocol to generate a functionally equivalent, yet syntactically or semantically different implementations of protocols. Introducing variations can prevent an attacker from devising a general exploit by analyzing one copy. More specific, network protocol vulnerabilities are nearly exclusively triggered via network input. Thus, it is reasonable to focus on deploying diversity within application components that deal with network communications. A CV reported the Eclipse Mosquito broker up to version 1.4.15 doesn't reject strings that are not valid UTF-8. The bug will disconnect other clients when they receive those invalid messages. By designing a malicious message, the attacker can attack every Eclipse broker with this version and cause vast disconnection. One solution is we can mutate the protocol to generate functionally equivalent yet syntactically or semantically different implementations of protocols. For example, we mutate the flags field in the packet generated by the weak version Mosquito, change it from 36 to a new value 70. And to be clear, this mutate will only change the syntactic format of messages. Both the client and the server will handle such changes accordingly to ensure the consistency and the correctness of this field's functionality. So by doing this, the original software has been changed. So does attack surface. the attacker will not be able to simply launch a simple same attack on different brokers. In our threat mode, there are two types of attackers, both armed with a standardized exploit and aiming at commandeering devices. The first type is the off-path attacker, who can send traffic towards potential victims and receive replies, but cannot observe the victim's communication with other nodes. The second type is the on-path attacker, who can send and receive traffic to or from victims, and observe communications between non-compromised devices prior to the attack. The attacker may use its on-path capability to reverse engineer wireless communications and identify vulnerabilities, so as to inject messages and better compromise devices. In this paper, we only focus on off-path attacker and leave on-path attackers as future work. To deploy diversity within network communication protocol applications, there are some challenges. First challenge is how to identify both code used to construct messages and parse them. It's important that changes must be correctly written into the outgoing packets and reversed from the incoming packets. The second challenge is how to keep any modification symmetric. In other words, we need to make sure changes in how protocol messages are generated must be reflected by changes in how the same messages are parsed. The third challenge is how to deal with reverse engineering. We can split mutations to two types, static and dynamic mutation. A static mutation is one which is statically embedded into the protocol firmware at compile time and always exhibit the same mutation. Static mutation can be reverse engineered by on-path attackers who can observe traffic. By analyzing traffic, attackers can know how to mutate on original message. And a dynamic mutation is one which can be enabled or disabled without recompiling the program by acting on appropriate control parameters. Thus, dynamic mutation is necessary to prevent inverse engineering. To solve these challenges, we propose an approach for analyzing and mutating network protocols in the IoT space. It can automatically diversify and specialize network protocol implementations. With our approach, we are not aiming to remove vulnerabilities from a code base. We are changing the control or data flow used to exploit some vulnerabilities. This is an overview of our approach. It consists of two systems, Paco and Aloja. Paco's full name is Parser Constructor Extractor, and Aloja is a mythical creature from Catalan mythology. It's able to shapeshift or mutate into a bird. At the beginning, Paco will analyze input program to extract useful information and output them to the next part, Aloja. And Aloja will do an advanced analysis and finish the mutation injection and mutants testing. Let's look at the Paco first. So what's Paco? Paco is a static analysis tool. It's a code understanding tool to locate network-related software components. It can extract necessary information for Aloja. The necessary information means those information that Aloja needs to finish the advanced analysis and mutation injection. Paco consists of three steps. First step, find network-related structs. Network-related structs refers to structs that are used to build or parse message packets. Paco first gets all structs from the application and remove non-network related structs based on the struct set, which includes standard library-defined structs like address information. Then it backward traces the arguments of socket read, write, send, receive, and or memory copy function calls to find structs used to store outgoing messages and incoming messages. Second step, Paco analyzes each function in the application to find all functions that are used to write or read network-related structs Paco found in the previous step. We consider these functions as network-related functions. The third step, PACO builds a graph to display relations between found functions and structs in the previous steps. Now we get to the second part of our whole approach, Aloja. Aloja is a static analysis and mutation injection tool that can further analyze information from PACO's outputs, inject mutations based on this information, then test and output useful mutants. Aloja consists of 3 steps. The first step consists of 2 small actions. Aloja first filters out unsported fields and corresponding parser and constructor functions. Then it refines the parser and constructor function sets based on the function level code graph. Sported struct fields refer to any fields fitting following rules. Rule 1. The sported field should have a data type that is sported by Aloja. Rule 2. The sported field should have both parser functions and constructor functions. To refine parser and constructor function sets based on the function level code graph, the key idea is to remove parser and constructor functions that are unlikely to directly affect protocol messages. More specifically, as shown in the example figure, Aloja will remove each parser which has a direct edge from another parser, and each constructor which has a direct edge to another constructor. In the second step, for each sported field and the corresponding parser and constructor functions, Aloja will generate all possible tuples. Each tuple consists of 1 field, 1 parser function, and 1 constructor function. Then for each PACO, Aloja chooses the mutation schemes and inject the code template into the original IR file, then output the mutant, which is a mutated IR file. In the Aloja, we currently have 3 mutation schemes: refactor global variable value, mutate field value, and encrypt field value. The last step of Aloja is correctness check. This check is to make sure each mutant Aloja outputs to the user is correct and useful mutant. There are also 2 rules for a correct and useful mutant. Rule 1, the mutant should keep functional integrity. This rule is to make sure the mutant can correctly work. Rule 2, the server mutant should block the message from unmutated clients. This rule is to make sure our mutant truly changes the messages and affects the communication. So how to do the check? Aloja first runs a mutated server and client to check whether they can communicate correctly. Then it runs a mutated server and an unmutated client to ensure that the communication fails. To evaluate our approach, we run it on 4 different IoT implementations. The results of PACO in identifying network-related structs are shown in the below table. False negatives come from network-related structs not being directly used for memory copy or memory operation or network operations. False positives occur due to PACO heuristics being misled by the presence of system calls that are frequently but not always network-related. Overall, PACO gets a higher accuracy, larger than 97%. The results of PACO in identifying network-related functions are shown in the below table. Overall, PACO achieves larger than 93% accuracy. Analysis of mistakes indicates that they occur due to mislabeling of the corresponding structs. To evaluate the mutation, we first did correctness evaluation. We run unit tests against the mutated version of each protocol. The results are shown in the below table. There are some failed tests. We manually go through each of them and rolled out these failed tests as benign, as they are our expected behaviors. Our mutation strategy is specifically designed to trigger failures like this. Besides, we also run fuzzing tests against the mutated version of Mosquito. The fuzzer ran for around 1 hour without triggering any unexpected behavior. We then did exploit mitigation evaluation to evaluate mutations. We reliably reproduced the 4 CVAs, 3 for mosquito and 1 for wakama. All CVAs are constructor or parser related, fit the focusing area of our approach. As shown in the below table, all these security bugs can be triggered by sending a designed malicious message. We tested the reported vulnerabilities before and after running our systems on the vulnerable version of applications. The results show that our approach can successfully mitigate all exploits we show in the previous slides by modifying the input necessary for triggering vulnerable code. And to be clear, our approach mutates the control flow necessary to reach the vulnerable sink instead of removing a vulnerable code. We also evaluated the impact of code graph-based filtering heuristics Aloja used to refine parser and constructor function sets. In total, Aloja generates 422 fewer mutants, which is around 25% of all mutants. Only 6 of them are useful mutants, which is around 33% of all useful mutants. We conclude that the filtering heuristic selects and removes incorrect mutations with reasonable accuracy. To evaluate the performance impact of our approach, we examined 2 aspects. First, the compile time overhead of running our systems. It's measured by timing the overall compilation without and with our technique, including Paco and Aloja. Second, the runtime overhead due to the additional computation performed by injected mutation templates. It's measured by sending 10 messages per client to the server via the respective protocol with 10, 100, 500 clients in the network. Each message is 10 kilobytes. The results are shown here. The upper table shows the incur compile time overhead for our approach and Ceylon. Most of increased overhead is due to the testing mutations in Aloja. For each possible mutation, Aloja must run the mutated application twice. The significant compilation time for Ceylon DDS indeed results from the fact that its large code bases induces many candidate mutants. Thus, then be voted on average tested a mutant requires 10 seconds. The process could be sped up by better mutation filtering heuristic, which we leave as future work. The lower table shows the overhead, a message send latency introduced by mutations. Results show that overhead is generally limited. Furthermore, the relative overhead generally increases sublinearly with the number of clients, and notably decreases in the case of Wakama when going from 100 to 500 clients. This fact in particular led us to suspect that 100 client Wakama results may be affected by an experimental artifact, but were not be able to trace the source of the deviation. In conclusion, we propose a technique for injecting mutations into implementations of embedded or IoT-oriented network protocols as a form of moving target defense. Our evaluation shows that our approach can correctly identify message-related code and inject mutations, which effectively prevents current exploits without breaking the protocol and only introduce limited overhead. Overall, we provide an important foundation for moving target defense based on protocol mutations, including the techniques and the libraries that can help more researchers and developers. That's all about my sharing today. Thanks for listening. Any questions or advices?